We usually think of change as this nice, steady, straight line. But what about things that just explode with growth or fade away in a huge rush? The world is absolutely full of this kind of rapid, non-linear change. And to really get a handle on it, we need a special kind of math. So let's dive in and explore the tools that help us make sense of it all.
And we're going to start with an example you probably ran into this morning, your daily cup of coffee.
Think about it, right? When you pour a fresh, hot cup of coffee, it cools down super fast at first. But then, as it gets closer to room temperature, that cooling process slows way down. It's not like it loses 5 degrees every single minute, nice and neat. Same thing with a car's value. It drops like a rock in the first few years, and then the depreciation slows. This kind of change doesn't follow a straight line. It follows a curve.
So that brings up a really good question. If it's not a simple straight line, what kind of mathematical tool can we possibly use to model that journey from piping hot to, well, just right?
Well, the answer, and kind of the hero of the first part of our story, is an incredibly powerful type of function built for exactly this kind of rapid change. So let's meet the exponential function.
Now, the most important thing to see here, the real secret sauce, is where the variable x is. It's not down on the ground like an x squared. It's up in the exponent. That is what gives this function all its power. You have a constant base, b, that's being raised to a variable power, and that's what creates those crazy growth or decay curves we see all over the place.
And this shows you the two main personalities of these functions perfectly. Over on the left, when your base is bigger than 1, you get this explosive growth that just skyrockets. But on the right, when the base is between 0 and 1, which, by the way, is the same as having a negative exponent, you get this rapid decay curve that plunges down towards 0 really fast.
Okay, let's quickly run through their key features. The domain, that's just all the possible x values you can plug in, is, well, any number you can think of. But the range, the y values you get out, is only positive numbers. See how the curve gets super close to the x-axis but never actually touches it? That's why we call the x-axis a horizontal asymptote. And one more thing, they all pass through the point 0, 1. Why? Because anything to the power of 0 is always 1.
So, exponentials are fantastic for telling us what the temperature will be after a certain amount of time. But what if we flip the question around? This brings us to what we call the inverse problem.
Let's go back to our coffee. We know how to figure out its temperature after, say, 10 minutes. But what if what we really want to know is the opposite? At what exact moment does it hit that perfect drinkable temperature? See, we're not solving for the temperature anymore. We're trying to solve for the time.
And to answer that how long question, we need a way to work backwards, to undo what the exponential function did. We need its mathematical partner. We need its inverse.
And that partner, that powerful tool for working backwards, has a name you've almost definitely heard before. It's time to introduce the logarithm.
Now, graphically, finding an inverse is actually beautiful. It's so simple. You just take the graph of your original function, our exponential curve, and you reflect it perfectly across that diagonal line y equals x. It's literally like holding a mirror right up to the graph.
And there it is. Look at that perfect symmetry. The reflection of the exponential function is the logarithmic function. They are perfect mirror images of each other. This one picture tells you pretty much everything you need to know about their fundamental relationship.
So, what does a logarithm actually do? Well, it answers the exact question we had about our coffee. If an exponential function says take this base, raise it to this power, and you get a result, the logarithm turns around and asks, okay, but what power did you have to use on that base to get that result? It's all about finding the exponent.
And this table just makes that inverse relationship crystal clear. Just look at how everything is swapped. The domain of one is the range of the other, and vice versa. The key point 0, 1 on the exponential becomes 1, 0 for the logarithm, and the horizontal asymptote becomes a vertical one. They are perfectly, completely flipped.
Okay, so we've met our two key players, the exponential and the logarithm. Now, let's actually see how we can use this awesome inverse relationship to solve some problems. And I'm going to point out a really common mistake you've got to avoid.
So here's a pretty typical problem. We start with this logarithmic equation, but to crack it open and solve for x, we use its inverse. That first step is the magic trick. We rewrite the whole thing in exponential form. The base, which is 2, raised to the answer, which is 5, equals all the stuff that was inside. So 2 to the 5th equals 3 times x minus 1 cubed. And from there, it's just algebra. We use the exponential to unlock the logarithm.
Now listen up, because this is so important. A huge mistake people make all the time is thinking that the log of a plus b is the same thing as the log of a plus the log of b. It's not. It's just not true. That property does not exist, and it is a trap that will get you the wrong answer every single time. Just burn this quote into your memory.
So, from your coffee getting cold, to how money grows with compound interest, to how fast information spreads online, this pattern of exponential growth and decay is absolutely everywhere. The big takeaway here is that exponentials and logarithms are just two sides of the same coin. They're a toolkit for understanding a world that's full of rapid change. So the question I'll leave you with is this. Now that you know the pattern, where are you going to see it next?